Hi, my name is Humaira. Next, I am going to talk about what is titration. So basically, titration is a method in which a standard reagent of a known concentration from a burette, the titrant, is added to a solution containing the analyte until the reaction between the analyte and the reagent is judged to be complete. Next, the purpose of titration. In general, the purpose of titration is to determine the concentration of the analyte in a solution by reacting it with solution with non-concentration, which titrant, until the reaction is complete by changing the color. In specific, it is to determine the content % of acetic acid in vinegar.
Next, basic components of titration, we have titrant, titer, indicator, and analyte. Titrant is usually known concentration solution to determine unknown concentration solution. The solution is volumetrically delivered to reaction flask from burette. Titer is the volume of titrant required to just completely react with analyte, and analyte is the species to be determined. Indicator is a chemical detector for protons in acid-base titration. It gives color change at or near equivalence point. It is also added to reaction flask to give signal when all analyte has reacted. Next basic components are endpoint, equivalent points, and blank titration. Endpoint is the point in titration where indicator changes color. It is also a signal that tells analysts to stop adding titrant and record final reading on burette. Equivalent points is the point at which an equivalent or stoichiometric amount of added standard reagent or titrant is equivalent to the amount of analyte. It is based on stoichiometric equation, and blank titration is titration of solution that contains all the reagents except the analyte. Type of titrations consists of two, which are direct titration and back titration. Direct titration is a direct addition of standard titrant to the analytes in the presence of acid-base indicator till the reaction is complete and reaching the equivalent point. It involves a single-stage titration, and we can calculate the number of moles of acid if the molarity and volume of base is known. Back titration is a titration where the concentration of an analyte is determined by reacting it with a known amount of excess reagent. The remaining excess reagent is then titrated with another second reagent. It involves a double stages of reaction, and the number of moles of acid can be calculated using simple subtraction of the number of moles of acid titrated from the number of moles of acid started with.
So now let's moving on to methodology. For this video, we use the experiment acid-base titration 1, the determination of % content of acetic acid in vinegar. For this experiment, the apparatus we need is 250 ml volumetric flask, 3 250 ml conical flask, 20 ml pipette, burette, heat-hot stand, and white dye. While for the chemical reagents, we use 3 brands of commercial vinegar. In this case, we use 1 brand only, sodium hydroxide pellet, and phenolphthalein. The preparation of NaO solution and standardization of NaO. First step is calculate the mass needed to prepare 250 ml 0.1 m NaO solution. Next, prepare the NaO solution by dissolving NaO in 50 ml of distilled water. Filter the solution into 250 ml volumetric flask, rinse beaker, and transfer the water into the volumetric flask. Add distilled water up to the 250 ml mark. Seal the volumetric flask and turn the flask upside down a few times. The third step is fill the burette with NaO solution, and then pipette 20 ml of the HCl from previous experiment into 250 ml conical flask. After that, add 2 to 3 drops of phenolphthalein as indicator. The fifth step is titrate the HCl in the conical flask with the NaO from burette slowly while shaking the flask until the indicator color change. Record color change and the reading. Repeat 2 to 3 times and record all your readings in the table. Last but not least, calculate the exact molarity of the NaO solution.
Now let's move on to the calculation. The standardization of NaOH solution. Mass of NaOH is 0.1 gram. This is our table. Final burette reading, initial burette reading, and the volume of NaOH used. We do this experiment 3 times raw, first and second. To get the average value of NaOH is 14.5 ml. The exact molarity of NaOH from previous experiment is 0.1 molarity. So first we need to find the mole of NaOH, which is volume of NaOH times molarity of NaOH. So we substitute the amount or the value of volume and the molarity, then the mole that we got is 0.0025 mole. Next, move on to the mass of NaOH. How to find the mass is mole of NaOH times with molar mass of NaOH. The mass that we got is 0.1 gram. Then we need to find the ratio of NaOH and HCl. Then we need to write the chemical balance, which is NaOH plus HCl then equal to NaCl plus H2O. Volume NaOH is 40.5 ml, volume of HCl is 20 ml, and molarity of HCl is 0.1 molarity. So substitute to the equation of MABA over MBVB equal to AB. AB is 1 over 1. Then we substitute the amount. The exact molarity of the NaOH solution is 0.013 0.1079 molarity.
Alright, now the determination of acetic acid in vinegar. First of all, pipette 10 ml of the given vinegar. First record the brand name of the chosen vinegar and dilute to mark with distilled water in a 100 ml volumetric flask. Second step, pipette 20 ml of this diluted vinegar solution into a 200 ml conical flask. After that, add 2 to 3 drops of phenolphthalein as an indicator. Third step is titrate the vinegar in the conical flask with the NaO from the burette slowly while shaking the flask until indicator changes color. Fourth step, repeat steps 2 and 3 2 more times. Fifth step, record your reading at the end point of the titration. And last one, calculate the weight volume percentage of acetic acid in the vinegar sample.
Okay, now let's move on to calculation of determination of acetic acid in vinegar. So first of all, we need to bring out the given information, and next the first step is to find the moles of NaOH used. Of course, 64 moles is mass times weight volume, and the mole that we got is 0.001436 mole. The second step is mole of CH3COOH in 20 ml diluted vinegar. So we need to bring out the chemical balance, which is CH3COOH plus NaOH, then CH3CO Na plus H2O. The mole ratio is 1:1. Then mole of CH3COOH is 0.001436 mole. The third step is moles in original 10 ml vinegar. Since 10 ml vinegar was diluted to 100 ml and 20 ml of the diluted vinegar was saturated. So moles in 10 ml original vinegar, 0.001436 over 20, then times with 100. Then the volume that we got is 0.00718 mole. Oh, sorry, not volume, it is mole. Then the fourth step is mass of acetic acid in 10 milliliter vinegar. Mass equal to mole times molar mass, so that the mass that we got is 0.4308 gram. Then the last step, weight over volume percent of acetic acid. We substitute the amount. Then the percent that we have is 4.31%.
Okay, so for my part, I will be explaining about source of error in titration. The first one, using contaminated solution. For example, when two different solutions are transferred using the same pipette and pipette is not rinsed with distilled water in between. For the second one, not filling burette properly. If there is an airlock in the burette, so-called, it can block the flow of the titrant, but it can also at some moment flow with the titrant. After that, we have no idea what was the real volume of solution. For the third one, transferring excess volume of liquid by blowing pipette, for example, by incorrectly labeling meniscus with the mark on the single volume pipe. For the last one, leaking burette. Sometimes burette leak slowly enough to allow titration, but will lose several tens of milliliters if left for several minutes after titer level has been set to 0 and before titration started.
Makes our lives easier. For example, we have food industry, pharmaceutical industry, and also cosmetic industry. Let's take a look at the food industry first. Titration is used in the food industry to measure the acid, base, and the salt content. For example, acetic acid in vinegar and mayonnaise, citric acid in orange juice, and also salt content in the food products such as chip. Next is the pharmaceutical industry. Pharmaceutical industry use titration to determine or measure the active ingredients and raw materials. For example, we have acetyl salicylic acid in vitamin C. It can ensure the right dosage were used and help to standardize the solutions. Next is water content that can reduce the effectiveness of the medicine over the time if there is too much or too low water. Okay, lastly is the cosmetic industry. Cosmetic industry use titration to control the pH, concentration, and also the amount of chemicals. For example, we can control the amount of pH level in the facial cleanser. Next is to control percentage the concentration of active ingredients such as EHA and BHA. And lastly is to measure whether heavy metal presents or not.
In conclusion, titration is a useful technique to determine the content percent of acetic acid in vinegar. The vinegar sample's acetic acid content can be accurately calculated by carefully titrating it against a standardized base solution like sodium hydroxide and using an appropriate indicator like phenolphthalein to show color changes when the reaction is complete. This allows for calculation of acetic acid concentration and subsequently the percentage by mass of acetic acid in the vinegar samples.